Hello everyone, today in this video I will be explaining class 12 unit 11 alcohols, phenols and ethers. In the previous videos I've completed the explanation on alcohols and phenols, and in this video today I'll be explaining ethers, the nomenclature, preparation and its physical and chemical properties. Now, what are ethers? Now, ethers are the organic compounds in which two alkyl or aryl groups are attached to a divalent oxygen known as ethereal oxygen. Now, we have a general structure of ethers as in this way. This oxygen is known as the ethereal oxygen. This is the general formula of ethers. There may be two alkyl groups or aryl groups attached to this our divalent oxygen. For example, we have here CH3 oxygen, CH3, or we can have another example, CH3 oxygen, C2H5. Now let's check out the nomenclature of our ethers. Now in the nomenclature, let's take this example here. Our first example, CH3O CH3. Now the common name here is that we have two methyl groups attached to our divalent oxygen. Therefore it will be here, it will be two methyl groups, methyl, and then ether, methyl ether. This is the common name, and then the isotopic name here will be, we have on both the sides the number of carbon atoms are the same. Therefore here will be one of the carbon atom here will be named as the methoxy. It will get the functional group name, and then the second carbon atom will get the parent name, that is methoxymethane. This is our isotopic name. Now at the second example, CH3O C2H5. Now if you check here the common name, here we have two carbon atoms, one carbon atoms. Therefore according to the alphabetical order, we have two carbon atoms. It starts with E and this is M. In the alphabet, our E comes first. Therefore the name here will be ethyl, methyl, ether. This is the common name, and then the isotopic name here will be this is our methoxy. This will be ethane. Therefore the carbon atom with the lesser number of carbon atoms will get the functional group name, that is our methoxy, and then two carbon atoms, methoxy, it will be methoxy ethane. Now another example, CH3O C6H5. Now here if we check the common name here, this is phenol, this is MP. Therefore M comes first. Therefore the name here will be methyl phenol ether. That is the common name, and the isotopic name here will be methoxy benzene. These are some of the nomenclature of our ethers. Now let's check the preparation methods. The first preparation of ether is from alcohols. Now how do we obtain ethers from alcohols? Here we will be dehydrating the alcohol to get our ethers. Now simple ethers can be prepared by the dehydration of alcohols by using our concentrated sulfuric acid H2SO4 at 413 Kelvin. At 413 Kelvin by dehydrating our alcohols. For example, if we have an alcohol here, it is dehydrated concentrated sulfuric acid at 413 Kelvin. We will be getting here ROR. With the removal of water means it is undergoing dehydration reaction. Example here, CH3 CH2OH with our concentrated H2SO4, and then here we will be getting at 413 Kelvin, we will be getting here C2H5O C2H5 along with the removal of a water molecule. Now if we check the mechanism of the preparation of alcohols of ethers from alcohols. In the first step, in step 1, the first alcohol molecule CH3 CH2OH non bears. Our high acid gives us a proton, and we will be here CH3 CH2OH positive. Now this in our second step. Now in the second step, the second alcohol molecule comes CH3 CH2OH and then reacts with our this CH3 CH2OH and here we'll be getting here our CH3 CH2O CH2 CH3H, and water is removed in this process. And then we are in the third step. In step 3, this molecule CH3 CH2OH CH3 CH2 CH3. This here will be having a positive sign. Now this goes, and then we'll be getting CH3 CH2O CH2 CH3, and then H plus is removed again in the solution. Now this is how alcohols are dehydrated to give here our ethers. This is known as our ethoxy ethane. Ethoxy ethane is obtained by dehydrating. We are taking ethanol here, ethanol, by dehydrating alcohol at 413 Kelvin in the presence of concentrated sulfuric acid. Now, however, at a different temperature, if we take here an alcohol CH3 CH2OH, an alcohol in our concentrated H2SO4, here the temperature, the temperature is increased to 443 Kelvin, instead of undergoing dehydration, here we will be getting here an alkene molecule here. An alkene is generated when the temperature is raised from 413 to 443 Kelvin. Now the second preparation method is the preparation of ethers by Williamson synthesis. That is also known as the preparation of ethers from haloalkanes, or Williamson's ether synthesis. Williamson's ether synthesis is the preparation of ethers. Now here, haloalkanes, when heated with sodium or potassium alkoxide, they give ethers. Now only primary alkyl halides, they give ethers. Now here, but whereas tertiary alkyl halides, they will give alkenes due to steric hindrance. Now firstly, let's check what is our Williamson's ether synthesis. Now the haloalkanes, if we take haloalkanes, react with sodium or potassium alkoxide. On heating, they will give us our ethers, and then NaX is removed according to whether we use our sodium or potassium alkoxide. Example here, CH3 CH2O Na, this is the positive negative part, plus we take our primary alkyl halide CH3 CH2Br, then we'll be getting here our CH3 CH2O CH2 CH3, our ethoxy ethane plus NaBr. Now this method is used for the preparation of both symmetrical and unsymmetrical ethers also, and it is advised that we use only for Williamson synthesis, we use only primary alkyl halides. Another example, we have here CH3 C, the tertiary alkoxide with our methyl bromide gives us CH3O C CH3 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 plus NaBr. This is 2 methoxy. We have here 1, 2, 3. Therefore here will be 2 methoxy, and then here will be, we have one substituent, therefore that is 2 methyl, 3 carbon atoms. It is known as propane. 2 methoxy, 2 methyl propane. Now however, if we use a tertiary alkyl halide, it will give us an alkene due to steric hindrance. Now if we check that our tertiary alkyl halide, CH3 CBr, CH3, this is a tertiary butyl bromide. When it reacts with RC2H5O, sodium alkoxide, it will give us CH3 C11CH2 CH3 plus NaBr along with C2H5OH along with alcohol. Now therefore, Williamson's ether synthesis is the preparation of both symmetrical and unsymmetrical ethers when haloalkanes are heated with sodium or potassium alkoxide. But one point to remember is that Williamson's ether synthesis uses only primary alkyl halides, which will give us ethers. Now we can use our sodium phenoxide also. Sodium phenoxide, RX, that will give us our alkoxy benzene, OR, and then NaX. This is known as our alkoxy benzene, and this is our sodium phenoxide. And therefore, these are the two preparation methods of our ethers. The first one is from alcohols by dehydrating the alcohols in the presence of concentrated sulfuric acid at 413 Kelvin, and the second preparation method is our Williamson's ether synthesis. Now, if we check the chemical reaction of ethers, now the first reaction is the reaction with HX, means hydrogen halides, and the second one will be studying the electrophilic substitution reaction of ethers. Now, reaction with HX hydrogen halides, when our ethers reacts with hydrogen HX, they will give us our haloalkanes, and then along with our alcohols. Now, if we have OR, alkoxybenzene, also react with hydrogen halides to give us phenol along with RX. An alcohol along with a haloalkane is generated when our ethers react with our hydrogen halides, that is HX. Now, for example, if we have here CH3O CH2CH3 reacts with H hydrogen iodide, we'll be getting here CH3I and CH3CH2OH. Another example, CH3COCH3, a tertiary ether reacts with our HI hydrogen iodide, it will give us our CH3OH, and then CH3CI-CH3, a tertiary haloalkane is generated. Now, if the second reaction is the electrophilic substitution reaction, of our ethers, we have halogenation, nitration, and Friedel-Crafts reaction. Now, if we check when our OCH3, this is known as our ANISOLE, anisole. Now, if we check the reactions, now firstly, let's check halogenation, that is bromine Br2 in ethanoic acid. In ethanoic acid, we will be getting two products. The alkoxy groups directs the incoming electrophile towards the ortho and it activates the ortho and the para positions. Therefore, we will be getting both a para product as well as a ortho product Br. This is our para-bromoanisole, and this is our ortho bromoanisole. The para product will always be the major product in every electrophilic substitution reaction. Now if we see here the nitration reaction, this HNO3 in concentrated H2SO4. We will be getting here also two products. One is the para product, and this is known as our 4-nitro 1, 2, 3, 4, 5, 6. This is 4-nitro-anisole, the major product, and then we'll be getting here the minor product, that is this OCH3 and O2. This is 1, 2. This is our 2-nitro-anisole as the minor product. Now if we check Friedel-Crafts alkylation and acylation reaction, now in Friedel-Crafts alkylation means addition of alkyl groups in the dependent ring. Now when anisole reacts with CH3Cl in anhydrous AlCl3, we will be getting here also a para product as well as a ortho product here, CH3. This is here, it will be here also 1, 2, 3, 4, 5, 6, 4 methoxy. It will be 4 methoxy. Sorry, here the numbering here will be, this will get numbering number 1, 2, 3, 4, 5, 6. Now here the methyl group gets the first number, therefore here will be our 4 methoxy toluene, and then the second minor product OCH3 and then CH3. This will be here with the methyl group will get the first numbering, therefore this will be 2-methoxydoluene. This group is known as our CH3 group attached to a benzene ring is known as the toluene, therefore the name here will be 2-methoxydoluene as the minor product. Now if we check here Friedel-Crafts acylation, it will be addition of acyl chloride CH3COC in the presence of anhydrous AlCl3. Here also we will be getting here a para product as well as an ortho product. Our para product OCH3, here we'll be adding COCH3, addition of acyl chloride. Here this will get the first numbering 1, 2, 3, 4, 5, and 6, and then our ortho product here OCH3, addition of COCH3. Therefore the name here will be 4-methoxy. This will be the methoxy group 4-methoxy, and this group, the COCH3 group attached to a benzene ring, it is known as acetophenone. Therefore the name of this compound here will be 4-methoxy acetophenone, and this will be 1, 2, therefore this will be 2-methoxy acetophenone. And in the electrophilic substitution reaction, the para product is always the major product because it has symmetry, and therefore this is the electrophilic substitution reaction of ethers. With this, I end the chapter on Unit 11, Alcohols, Phenols, and Ethers.